We are delighted to see your enthusiasm, active participation, and commitment throughout this exciting journey of learning and innovation. Today's workshop will provide participants with a broader understanding of advanced IoT technologies and product development. During this session, you will be introduced to topics such as PCB design using KiCad, embedded Linux concepts, AI integration in IoT through TinyML, and industry IoT architectures and deployment pipelines. By the end of this workshop, you will gain an understanding of product-level IoT development, basic PCB design workflows, and how technologies such as AI and embedded Linux fit into modern IoT ecosystems. We hope today's session will inspire you to continue learning and developing innovative solutions for real-world challenges. Without further delay, let us begin today's workshop. It is now my great pleasure to introduce our speaker for today's workshop, Mr. G.S. Umair Ahmadh. Mr. G.S. Umair Ahmadh holds a Bachelor of Science in Engineering in Electrical and Electronics Engineering from the Southeastern University of Sri Lanka and is currently pursuing a Master of Science in Engineering by Research. He is an electronics engineer and currently serves as a visiting lecturer at the Faculty of Engineering, Southeastern University of Sri Lanka. He also has valuable industry experience as a former senior applications engineer at Synopsys, with both academic and industry expertise. Mr. Umair Ahmadh has a strong understanding of electronics, embedded systems, and modern engineering practices. We are truly honored to have him with us this evening and look forward to learning from his knowledge and experience. Ladies and gentlemen, please join me in warmly welcoming Mr. G.S. Umair Ahmadh. Sir, the virtual floor is now yours.
Hello, thank you, Situ. Thank you. Okay, so let me thank you, organizers, for allowing me to share this time with you guys, sharing the knowledge and expertise and my experience from prototype to real products in the IoT. Okay, let me share this screen and then get to. Okay, give a second. Please confirm once you see the screen, okay? I hope you can see the screen now. Hello, can someone confirm, please?
Yes, it's visible.
Okay, sorry. Okay. Okay, so let me just start with this. I think our scheduled time was around 7. Anyway, let's try to cover as much as possible. So I'm not sure how much things I can cover into this, but let's try to cover as much as possible. So I will be focusing more on getting a prototype IoT hardware into making it into something that you can actually sell in the market, a production level hardware, right? So that's the focus of this workshop that I will be doing. I will also be giving you some idea behind prototyping and what are the things that we will be looking into. What are the issues we will be facing when we actually take our things to the actual market? So anyway, with a formal introduction, apart from the formal introduction, the organizers have given about me. So I have been in this industry, electronic design and software development industry in the past more than 6-7 years. So I have done prototypes, I have done actual production level products. I have shipped many products and I have gained enough experience to share with you some real world problems with you. So currently I am working with a couple of companies on product development, hardware, IoT, software, and AI products as well. So that's a quite background on what makes me qualifying enough to talk about these stuffs, right? So anyway, moving on. So these are the couple of things that I'm planning to talk in this session. So first of all, sorry. Okay. Yeah. Anyway, let me just talk through a couple of things. First of all, you have an IoT product, right? So let's how is it? Okay. So once you get an idea for a product, for example, you get an idea to build something, an IoT hardware product, or you get a customer inquiry, right? A customer is asking, they want something, they want a product. For example, let's think about a real world example, maybe a cold storage monitoring system, right? For example, you have been reached by a client, a pharmaceutical client. They transport medicines, right? So this medicine has to be stored in a set of temperature range, maybe like 4 degrees Celsius or minus 10 degrees Celsius or 0 degrees Celsius. It can't be kept outside of this temperature range, right? So when they're transporting this medicine from Colombo to somewhere in the parts of the island, for example, the south, Gaul, or to the north, Jaffna, or to the east, wherever they are transporting, like 4 or 5 hours of transporting. Let's say they are keeping that medicine inside this refrigerator, inside their vehicle. The driver is driving the vehicle. They don't know what's happening in the back, right? What happens if the refrigerator fails during the travel? The medicine is spoiled, right? So this customer wants to have a device added inside their refrigerator so that they can later check the logs to see if the temperature range was achieved throughout the journey or was there some failure, right? So this temperature logger needs to be there. So this is customer's requirement. So that is the first step, right? The customer is telling you, we have this problem. We need a device so that we can put there, right? So once the customer says that, you don't just get into the product development stage. Yeah, I'm going to do this. I'm going to put this microcontroller. I'm going to put this circuit design and that. No, the very first step into designing a production level hardware is to understand customers' requirement into something workable, right? Because customers are not technically sound. They will have business ideas. They will have different background, right? So your duty as a hardware development engineer, right? The first step is to validate their ideas, validate their concepts. So now they say they need the product, this temperature logging system, to be inside their refrigerator. So then there are a couple of questions, a lot of questions coming in, right? For example, how are we going to power this device, right? First step, how are we going to power this device? Are we going to put a battery in, right? No, he will say, no, we can't put a battery because the battery is, the device is going to be kept inside the refrigerator. The refrigeration temperature is going to go below zero degree temperatures. So the battery chemistry has to be decided there, right? So that's going to be a problem. Can you use lithium batteries there? Or are you going to use lead acid battery there? What kind of batteries are you going to use? There will be problems, right? So now there is another customer saying they don't want to have battery. They want to power it from the vehicle itself. So then there are other problems going to come in. So you are going to evaluate all these requirements to finally get the final requirements finalized, right? And then there is another problem coming in. Is this going to be an offline device or is it going to be an IoT device? Because are you going to check the temperature logs only uh, after the travel ended, or are you going to like monitor it live, right? Do you want live monitoring of these temperatures inside the fridge? So once there is something wrong happen, for example, the refrigeration power has gone down, you get an alert to your phone. the owner's phone or the manager's phone that this something has happened, so that they can call the driver and say, what happened, check it, so they can check it now, right? So these kind of requirements we need to analyze first. So that's the very first step. So that's the requirement gathering. So basically, this is the V-shaped steps or flow to get our products right. This is basically for we use for softwares mostly, but let's try to adapt this to our hardware thing. Okay, so that's the first step. Okay, so before we come to the prototype part, we are talking about the customer requirements part. So if you don't have an actual customer, there might be, I mean, you might be the actual customer. For example, if you have an idea, you want to develop this product and then sell it to the market, right? Now you are the customer. So now you have put yourself out there and then read your requirements and then finalize it. And then you are going to analyze it and then finalize it. So that's the very first step. If you miss this part, this prototyping or the product development journey is going to cost you a lot of money, a lot of time, right? And there are a lot of chances you will fail. Okay, so that's the very first thing we need to do. Okay, now let's finalize our design, finalize our requirements. Now we are good. Now move on to the system analysis. So system analysis in the sense. Now let's say, okay, so to analyze our requirements, we need to first prove that our concept is going to work, right? What kind of concept do we have? So now we have the customer requirements. Now we have a lot of source coming in. Can we use this? Can we use this hardware? Can we use ESP32 or Arduino board? Or are we going to use Raspberry Pi for this? Or are we going to design a custom circuit board for this? If we are designing custom circuit board, what kind of chips are we going to use? What kind of other components are we going to use? How are we going to power it? What kind of wireless communication are we going to put in? Are we going to put Wi-Fi? Are we going to put Bluetooth? So those are different things, right? So now these are all defined in our requirements. Now we need a proof of concept. We are going to make something that is very minimal, that's going to work. Okay, we are not going to put kind of colorful design. We are not going to put something very good looking. Nothing. This is just going to work. Okay, so this is we are going to define what is the architecture, and then we are going to choose the right development path. Right. So at this stage, you might use bare breadboard. Yeah, you can start with your breadboard. You can put together some ICs, put together some wires, and get everything done. You might have already done it, right? So that's why I'm not going to go deep into those parts. And then you have everything in your desk with some power supplies. Everything is there. You put you check with the temperature. You try to read it from the memory. You try to connect with Bluetooth and read it through your mobile phone. Check some alerts. So, yeah, these basic features you're going to test if it is going to work. Right? That's what we say. Proof of concept. Is the concept workable? Is the concept achievable? So that's what you are trying to do with your proof of concept. Means we call it POC, right? And then this proof of concept will also tell you the feasibility. What is feasibility? Is this something doable? Is this something achievable? Will this work? Not only that, we will also be checking, is this going to come under the budget, right? For example, the requirement says, we need this, and then you try to achieve it in the proof of concept. But when you do that, you realize that the particular component that you need for this purpose is going to cost you more than the budget is going to allow you, right? So that's going to be a problem. So these are the things that you are going to check at this stage. So that's the first step, the phase one of product development, right? And then now let's say this is the temperature logging system that we are going to design. Now, okay, now the customer has finalized the requirements. Now we are tasked to get this done, but we have some money received as well. So how are we going to do it, right? At this stage, now we have breadboard or everything, whatever the things that we are going to use. Now we need to choose our development platform, right? So the first stage, we are not going to go for the custom PCB design. Rather, we are going to choose whatever is currently available on the market, right? Off-the-shelf products. We are going to buy it and then make it work. So to do that, we need to decide, are we going to use a microcontroller or a microprocessor? So do you know what is a microcontroller? What is a microprocessor? Something like Raspberry Pi, we call it microprocessor. Why? Because it has a processor, an external memory. It's like a computer. It's like a system on chip, right? But microcontroller is something enclosed. The processing part, the memory, everything is enclosed inside, so it can work standalone, like your 80 mega microcontrollers, ESP32 microcontrollers, right? So these are the things. So how are we going to use it? How are we going to decide which one is going to be your use case for this development, right? So power is the most important thing you're going to decide. For example, if this is a battery powered device, right, you can't put some high energy consumption devices because, for example, a Raspberry Pi or BeagleBone hardware or any other Jetson or whatever the systems or microprocessor based development boards you have, they are going to be power hungry. They will be demanding more energy. So if your design requirement doesn't need that kind of processing power, let's skip that part, right? Let's not use that kind of processors. Rather, stick with microcontrollers because our system is now defined. We are going to read the temperature, we are going to read the humidity, right? And then we are going to log it and save it to the local storage, memory card maybe. Also, we connect to the Wi-Fi or connect to the 4G LTE or cellular network, and then keep updating this data to the server. This is the basic requirement. Can we do this with a microcontroller? That's the question we ask at the prototyping level. If we can do this with a microcontroller, we will use a microcontroller. Are there something more processing power needed? For example, are you using some computer vision? Are you going to use some AI processing? Anything LLM needed or something machine learning processing needed or basic computer vision needed? Then you go for something more processing power devices, for example, a Raspberry Pi, right? So that's the first stage we decide. Okay, now that we have decided these types of components, we make our product, the prototype, the first proof of concept product, right? Right. Now, once we decided what is the development platform we are going to use, there will be problems, right? So now we decided these products for the prototyping phase. At this stage, there will be a question. We can't use the same platform for the final product. Why? Why can't we use it? This is the problem. For example, let's say you are doing a prototype with an Arduino board. The cost is very low, right? You can buy an Arduino board for like 1,000 rupees or 2,000 rupees and then get your prototype working, right? But can you use this for let's say the customer is ordering 1,000 units, right? 10,000 units. Can you use the same board? No, you can't use it because the end product needs to be smaller in size, lower in cost, right? And it has to be something production looking, right? You can't put a big, large microcontroller board inside it, right? So initial cost is going to be low for Arduino like board. For system on module like Raspberry Pi, the cost is going to be higher, right? If you're going for custom PCB design, it's going to be really high for the initial cost because you're going to design the PCB, order the chips, get it assembled, and then finally fix it in your product. So that's going to be high. But when it comes to scaling, right? Whenever you design a product, whenever you go into production business, you need to think about scaling. If you're going to make only 10 products, okay, that's fine. But if you're going for 10,000 products, 1 million products, then you need to think about scaling, right? When you are manufacturing in bulk, you need to think about scaling, right? So let's say you are manufacturing 100,000 products. At that point, using an Arduino board or development board is going to cost you very high. Using a system on module like Raspberry Pi is going to be below the cost that you're going to use an Arduino board. Why? Okay, and then we talk about custom PCB development. So when it comes to bulk development, bulk production, custom PCB design is the affordable way because you can make your 100,000 PCBs and then you can source all the components in bulk, wholesale price, and then get your things done. But the system on module or development boards, these boards are produced by someone else and then being sold in the market, right? So this is going to cost you more. That's why for bulk products, we are going to design our own PCB. For prototyping, we are going to use a development board. For low count products, for like sorry guys, I think the connection lost. Okay, hope you guys can hear me now. Okay, I'll continue. So the time to market. Now the customer says they need the product in like 10 days. You can't go for custom PCB design. You need to go with something readily available, like a microcontroller board or a system on chip board like Raspberry Pi, right? So that's going to be your decision. Also, there will be something called certification, right? Certification is going to be something really important if you're going to sell this to a market. For example, if you're selling it to the medical market, or if you're going to sell it to food market, right? So you need different certifications. So these are some stuffs, very important stuff you need to consider when deciding what are the components you are going to use. So when deciding this, you're going to consider all of these things. There are a lot more things, but these are going to be very important things as well. Okay, so now let's move on to, right? So now let's say we finished the breadboard, jumper wires, everything. Now we are going to make a what we call the validation test, right? At this stage, we are not going to build something that is going to look better. Rather, we are going to make something that is working, like a minimal working prototype, right? So the MVP, the minimum viable product, that's what we are going to design at this phase. Let's try this, for example. Now, at this stage, let's say so at this stage, we can go for the PCB designs because in the first phase, we have finished using this kind of I think I have skipped many parts here. Okay. So initially we had a breadboard, jumper wires going everywhere. So our initial product is working in your desk, right? You can't give this to the customer saying this is working, right? No, you can't do this. Maybe you can use it for proving your concept. Now, so the scaling I told you about, the average time to market in the hardware product industry is around 42 months. It's around like 4 years, right? So that's a very long time. But for software, what you can do is you can design your software, you can ship it overnight. When something goes wrong, you can give an update tomorrow, it's going to work. But for the hardware, you can't do that, right? It's going to be a long time from the system requirements to getting everything finalized, everything tested, everything designed, everything into custom PCB, chip design, antenna design, everything. It's going to be a long time, right? So you have to go through this validation every time. So let me show you some kind of examples. For example, let's say you are designing a watch. What is the initial step? You will have a testing setup like this with some display, power supply, everything's there. So once you have everything done, you will move on to this kind of PCB design, a kind of a minimal viable product PCB design, right? So let's try making one. Once everything is finalized, this will be our end product. So what are the skills do you need? You need to have a good PCB design skills. Also, you need to have good CAD skill, the enclosure design skills, the 3D modeling skills, right? So, for example, the Oculus Rift, the VR glasses company, they used some kind of duct tapes and everything and for the first prototype, right? So they made it working. They showed it to customers and then got the investors and then they finalized their design. So that's how we are going to do it. Okay, now let's try some PCB design first at this stage, the validation test, right? So there are a lot of PCB design softwares used in the industry. The Altium is the most premium, high-priced professional software. There are other softwares as well. Pads are there. Cadence has some softwares as well. But mostly used these days, KiCad is one of the mostly used softwares because it's free and available to everyone. Also, it's very professional. It's industrially accepted software as well. But for this stage, we are going to use something really easy, ECEDA, right? Okay. pro.eceda.com. ECEDA Pro. This is a software, an online PCB designing software that I'm going to use for this demo purposes because it's pretty good software, right? It's pretty good for entry-level PCB designing purposes. One of the most easiest thing is going to deliver us is the component selection, right? Because let me go through this, okay? So I'm going to use the online version of it. Let's try some demo hardware board and see how are we going to order it to get our physical hardware manufactured and what kind of problems are we going to get during this design, okay? It's taking some time to load. Um, just taking some time. Okay, maybe while it loads, let's okay, let's see what kind of hardware we can design for this demo so that we can do it. So this is how I do it when it comes to PCB design. Okay, so first, once we have the circuit requirements, I use this tool called draw.io. I use it for diagram purposes, right? Okay, now let's see, we are going to design maybe an LED controller, right? Let's use this. I already have some designs I can show you. Uh, Maybe I'll show you a new design. It's taking so long to load. I'm not sure why. Usually it's faster. So let's say we have a product. We need a product to design, right? So this product, let's say our temperature logger that we talked earlier, right? So this is going to be the product. So this product needs some power. What kind of power are we going to use? Let's say we need a battery. Can we design the battery inside the PCB? No, right? We need to connect it to the PCB externally. So let's say this is the battery that we are going to connect to the board. So if we are attaching this battery, it needs to be charged, right? It needs to be charged. So we need a battery management system that is going to take the power and charge the battery, also take the power from the battery to power this board. So we are going to connect this to the BMS. So how do we charge the battery? Are we going to plug out the battery outside and charge it and put it inside? Or are we going to put some USB port here so that you can plug it and then charge it? So now let's say you have a power circuit, power adapter, USB charger, right? Now you're going to put a USB port here, right? So USB-C, right? You're going to plug in this charger here. This is the USB-C port. This is going to give the power to the BMS, and then BMS is going to charge the battery, right? And then when we need the power for this hardware, for this board, this will draw the power out from this battery and then give it to the main controller. So what is let's say we have a microcontroller board, maybe ESP32, right? So this board, this controller that needs the power from this device. Okay, so when we use this USB-C to charge the battery, there might also be another case where we need to program this MCU, right? So we need a way to connect this USB-C to the MCU as well. And then this MCU, the microcontroller unit, is going to be connected to the sensors. What types of sensors are we going to have? Let's say temperature sensor. So are we going to put the temperature sensor on the board, or are we going to connect an external sensor outside? For example, temperature monitoring controller. Let me show you something. For example, this device, you see here, this is the temperature probe, the sensor, actual sensor, they have connected it outside. So this will be powering this board. They're not having a battery, right? So this is one type of controller. Otherwise, there will be some other boards where you actually have the sensor on the device itself. So that kind of decisions we are going to make. Let's say we are going to connect a temperature and humidity sensor here. And then let's say this sensor we are going to connect outside. Right. And then this sensor data is going to be connected to the microcontroller. Once we read this data, we need a display on the device itself, right? So LCD display. So this is going to give the data to the display. Sorry. Right? This LCD needs power from the BMS. Right? What else do we need? This MCU, ESP32, already has Wi-Fi and Bluetooth. So that's our resolved problem. So this is what we are going to design in the board, right? So shall we do it? Let's see. Okay, so let me open up a new design. Let's say TH logger, right? You can, I mean, the basic PCB design flow is kind of similar in all the software. If you're using KiCad or you are using Altium or whatever the software, the fundamental concept is going to be the same, right? So initially, let's go through some real world problems that we are going to face during our designing phase. Maybe we will spend some time in this stage, and then let's go to the next steps eventually. I don't know, this is really slow this time. So this is the first step we do because we need to understand the overall, the high level structure or the diagram or the outline of what we are going to actually design. So when you do this, you also have to define or decide what kind of board size are you going to have? Are you going to have it like a really big board size, or are you going to have a really tiny size? And where are you going to put these ports, right? Because this entire hardware is going to go inside a refrigerator. There will be water inside it, right? You can't allow water goes inside these ports. So how are you going to decide it? So you need to decide what components are you going to use. So that's what we are going to use here. It's really, really tough. Let me see if I have prepared. I chose ECDA because it's quick, fast, and easy, but it's kind of messing up this thing. Okay. Okay, while it loads, we will come back to this and continue the PCB design part. Okay, so once we get the PCB design, we will have a work-like prototype, something that works. But when you get the PCB, there might be like you design something, but there might be issues in manufacturing, or you made some mistake in the design. So you need to tinker with your PCB to get it working as well. We will look into it. Okay. And then, so this is the PCB design. So when you design the PCB, you need to have multiple layers. You can't do in a single layer in most of the cases, right? What is layer? Let's see here. I could have. You see here, for example, Yeah, this maybe this way. Okay. So you see here, you will see a top side of the circuit board. Also, you will have a bottom side of the circuit board. Those are visible layers. There will be also internal or inside layers in the PCB. Each layer you will use to design your lines, power lines, signal lines, everything. You will be laying them out, right? So that's very important. So we have it. So that's very important. So how are you going to design it? For IoT boards, usually it's 4-layer, 6-layer boards are there. Okay. And then RF designs and traces. This is going to be IoT means we need the radio frequencies, the Bluetooth, Wi-Fi antennas need to be there. So how are you going to trace them? How are you going to put them in your board? How are you going to design it? That's very important. And then the thermal management. How are you going to, because the microcontroller, the MCU chip is going to get put out some heat, right? So if you put some other components around it, that will be so cluttered, and then the thermal management will be a problem. So you need to decide to place where to place which component. Also, how are you going to plan it to dissipate the heat from the controller? For example, in your computer, inside the system unit, you can see there will be heat sink. In many motherboards, you will see heat sink. The aluminum metal device is mounted on top of the chips to dissipate the heat. Do we need that here? You need to decide. If it is a power electronics chip, you really need it. If it is a power MOSFET, you need it, right? So those are the components that you're going to decide. And then you need to, so this is a really important concept, DFT, design for test. The thing is, you are going to design not the final product, rather this is going to be a prototype. There is going to be a minimal viable product, right? So this product is going to have a lot of problems. It will not work in the first run. So that's why we have this concept called design for test. The design is going to allow you to test it. Once you have the board, you should be able to test it, right? So you have to design it so that you can test it. Don't design it and then find a way to test it. Rather, make your design in a way you can test it. So that's that's the basic idea behind the design for test, DFT we call it, right? The thing is, when it comes to large level hardware design, hardware product development, each of these coming under different teams. RF engineers are there to do only this part of the circuit design. Thermal engineers, the thermal power related engineers are there to handle that part. You will have DFT engineers are going to be in the team to ensure that this board is going to be DFT suitable, right? So these are the important things that you are going to have in mind when you design your circuit. So let's try. Now, the very first step is the overall system diagram. The second thing is we are going to draw the schematic. What is the schematic? You all know the electronic schematic that we are going to draw. So how are we going to do it? We are going to use it not with a pen and paper. Rather, we are going to place the components from the library and then use it here so that we will have our circuit ready. So first of all, we have two parts here. In a single board, the board that we are going to design, we have a schematic and a PCB. The PCB file, that is the actual final output, right? So this will be the electrical definition of which component is going to be connected to which component on which pins. That's important. So let's see. Now, the very first component that I'm going to place in this board is the microcontroller. Now, what microcontroller? So I will go here, place, and then device, we use block, and then come here, and then I have a couple of options. If I'm going to use this LCSC is a part supplier, you can see. You can buy components from there, right? If you are going to order this PCB from companies like JLC PCB or PCBWay, these are some Chinese PCB manufacturers, they will help manufacture our boards. this is a quite easy way to do it. Directly, we can order from them, right? So now let's say I'm going to search ESP32. Which components I'm going to use? When I search for it, I have a couple of things to check. For example, let's say I use this component, ESP32. Yes, sir. Let's look at this component part number later. Now let's see. LCSC has 17 in stock. They only have 17. Let's say if I use this component in my design, and then the customer is ordering like 100 units, can I order this part? No, because they only have 17. Then I have to go find some other supplier for the remaining 83 units, right? That's going to be a problem. So I need to choose a component that is widely available. So I'm going to filter it, sort it by stock. Now you see this ESP32 S3 is having, I mean, they have a lot in stock. 21,000 they have in stock, right? So that's quite a good thing. So this thing, JLC PCB has 54,000, right? Now I'm going to choose this microcontroller. So there are different versions, ESP32 S3, ESP32W room, right? ESP32 C3, many things are there. You can read the data sheet to check what is the exact board you need, right? So I'm going to use this. I'm going to maybe ESP room. Okay, I'm going to place it, right? So now I'm going to place it in my schematic first. Now, let's say I'm going to place it somewhere here. So this is my schematic. Now I press escape. Now this is here. But the thing is, I don't know which pin is for what purposes. So I need to read the data sheet. I can right click on see the view data sheet. Probably this will be in Chinese. Anyway, let's see. Okay, now what I'm going to do is I need to power this. Let me place all the components that I need first, and then do the things that I need. So I need a connector to connect the temperature sensor, right? What kind of connector can I use in this board? So that's a different section, right? There will be a lot of connectors. For example, these types of connectors are there. These types of headers are there. Male headers, female headers. You have wire screw terminals are there, right? Let me try to use some screw terminals. Let's see if I have some screw terminals in the library. I'm going to search screw. Yes, they have this screw terminal. I'm seeing they have a lot in stock. The price is also good. If I purchase 5 units, it's 0.1 units. So I'm going to use it. So this is a 2-pin connector. Temperature sensor is, I'm not sure. Let's see what temperature sensor I'm going to use. So there are a lot of sensors. For example, this DS18B20, that's a good sensor, right? So the thing is, we need to decide the component. For example, when we check for the temperature sensor, we need to check this temperature range, because this is allowing us from -55 to 125 degrees Celsius. Our use case in the refrigerator, we are going to go below the 0-degree temperature. And then we will not be going to this much of temperature, but that is giving us a fair range to work, right? So this is fine. We can choose this temperature. Also, the usable voltage range. This is an important thing to consider, because in our system, this microcontroller ESP32 is going to work in 3.3 voltage range. The USB is going to give 5 voltage range. So this is the voltage range that we're going to work. So can this temperature sensor work in this range? Yes, it's going to work in the 3.0 voltage to 5.5 voltage. So that's going to work in our 3.3 voltage range as well, right? And then the stainless steel tube, that's good. Cable is 91 centimeter long. Yeah, that's good. And also check the terminals. It has a plus voltage, a ground, and then the data signal terminal. So it needs 3-pin terminal. So let's use this 3-pin connector. So I'm going to get rid of this and then place a 3-pin terminal. So this is a 3-pin terminal. They have quite a lot in stock. So I'm going to place it. So this is a kind of a quick prototyping session. So don't think too much about this, right? So I'm going to place it over here. And then what else do we need? In our system, we have a USB-C connector. So what kind of USB connector I'm going to use? Let's see USB and then search for it. In most of the times, you will need to go with specific part numbers, but this is a quick session. We don't have much time to go through that. So I'm going to go into this kind of session, right? So this is quite cheap, and then also it has widely available stock. So I'm going to use this. This is going to be the USB connector. And then what else do I need is the battery management system. What type of battery management system I need? There are quite famous popular ones, BMS chip. So we can quickly Google it and get some really good senses. But the problem is BMS power management circuits, these are not like single chip, right? They come with some other peripherals, other associative hardware components. For example, the Texas Instruments has a lot of good things. For example, USB-C. Okay. I think there will be something BQ3, something like that. Okay. Is my internet slow or I'm not sure, man. Okay, I think this chip is good. I have used this chip before. Let's see if they have it. Yes, they have it. So let's look at the data sheet and then place it. So the data sheet, this will tell us how to design this. So let's look at this circuit. So here you see, this is the chip we are going to use. It needs some MOSFETs, right? And then it needs an inductor, right? And then it's going to get the input. This is going to go to the battery and it's going to go to the output. So this is going to be a tough part to be very careful about to get the design circuit running. Usually, the data sheet is going to give you application circuits. This is an application circuit. For example, here, this application circuit is going to tell you what is the value of the capacitors you're going to use, what is the value of the resistors you need here, what type of MOSFETs you need, what types of inductor you need. Everything is listed for a particular use case. You can fairly rely on it for your prototyping purposes, right? So I'm going to skip this design part in this because of the time constraints. Now, let's say once we have placed all the components that we need, we will be connecting. For example, this plus is going to go to the power. Maybe like I will use this power symbol, right? And then I will use this to connect it. The same power we are going to use for the USB as well. And then I'm going to use the same VCC here. Sorry. And then same power, the same thing is going to power the battery management chip as well. And then I'm just going like randomly, okay? I haven't checked anything correctly. This might be wrong as well. So the ESP32 chip is going to get VCC 3.3 voltage, let's say. The BMS might be giving 5 volt. There may be problems. So we are going to, I mean, we will be taking care of it in the actual PCB design. So this kind of a quick walkthrough. So please don't mind about this. And then we need a ground. And then we need a ground here. We need another ground here. And then place it. And then this temperature signal, let's say we are going to connect it to our pin number 18, right? These types of connections are there. We have a TX and RX pins. We are going to use this the USB-C to connect to here, right? Those types of connections you do, and finally get your the circuit design. Once you have everything, what you're going to use is you're going to go to the PCB board to get your work done. So now design, update, convert schematics to the PCB. So we have all the components placed, all the electrical data signals connections done. Once everything is done, we are going to update this to the board. So update, convert the PCB. Now we have the PCB loading from the schematic that we drew. It's kind of updating, downloading everything it needs from the circuit. It's kind of slow, but you see. Why is it taking this much time? Okay, like we finished the schematic part. Something very basic. Okay, I didn't go deeply. There are a lot of things to consider when designing this. Okay, so so this component sourcing reality, this is an important part. So you might have noticed that when we selected the components, we looked into data sheet, we checked if this is stock available, is the price good, how long they can take to get us the components we need, because you see here they have available 12,000, and then estimated lead time is 3 to 4 business days. They can give, if we order in bulk, they can give the component. But if you choose some component that is not available, it happened during the COVID period, the semiconductor shortage happened. Same thing is happening this time for the memory chips. RAM prices are getting high because these are being heavily used for AI, and consumer products are not getting the enough memory storage devices readily available. So if you design using one such chip, and then finally when you go for production and the chip is no longer available, then you need to do the entire circuit design again if you don't have any replacement parts, right? If you can't switch to some other parts without having to edit your circuit, then you're doomed, right? So that's why we try to stick to some commonly available parts as much as possible. So that's one important thing. So end of life next month is it's like, if the chip is going to be end of life, if the company is no longer going to manufacture the chip, that's going to be a disaster for your product. So that's why we always need to design with a secondary or alternative footprint in mind, right? So if this chips goes obsolete, you should be able to quickly find some other chip and get on with your product. And then moving on to the next thing, the design validation test. Before coming to this, I think we should be able to get the PCB done. Why is it taking this much time? While it does its thing, let's move on to this step. So now we have the validation test. We design the circuit board. We send it to the manufacturing. We have it like we use our power supply, get everything done, right? Everything's working now. Okay. Let me show. Maybe let me show you like because it's taking too much time. Uh, this is something I actually shipped for a customer. He was a US-based customer, I think. He is kind of a LED wearable device. We actually manufactured it, and then the customer received the board. But this is taking too long to load. Okay, while it loads, let's look at the thing. So next step will be design validation test. Now we need to go to the design validation test. What is the design validation test? Earlier, we checked if it is working only. The board will be looking ugly, right? So basically what you will have is something like this. You have the PCB, you have wires going around. That is the validation test, the engineering validation test. Now we move to the design validation test. So earlier it was like work, or the working is fine, working part is fine. Now we are going to design the looking part, how it's going to look, the final look, the enclosures, the outer design, how it's going to put some LEDs, how is the display is going to work, those kind of things, right? Most importantly, the harsh realities of the physical world, right? So you're going to put it inside the refrigerator. Or if it is a device that you're going to put in the automotive, in a car or in a lorry, right? There will be devices that you might design for some maybe like underwater use cases. So whatever the use case is, this has to work. So that's what we are going to test at this stage, the design validation test. So what types of tests we do is, there are a lot of tests. The first test will be the environmental test. We put it in harsh environments to the temperatures, high temperatures, low temperatures, and see if the circuit is working. If it's fine, we do some EMC RF test as well. What kind of test? For example, when a human touch the board, it's going to give some the electromagnetic interferences. So if that interference is going to make your circuit fail, then the design is not going to make it to the market, because there will be people touching this device, right? When they touch, they don't get the shock. The devices should not fail. So that kind of test we need to do. Also, the mechanical stress test. Sorry, I forgot some images here. This device might be falling, dropping, getting pressed by some other stuff. So the mechanical stress test we need to do. So this, have we got this? I think yes. Okay, so this is one of the design that I did for a client. So you look here. So I have used ESP32 C3 Mini here. So this design, right? So it needs power. So I have given 3.3 voltage power here. But this 3.3 voltage power, according to the data sheet of this, it needs some capacitors to filter out noises, all right? Filter capacitors. So this 3.3 voltage, if there are noises coming in, it will be going through this capacitor. If you don't know why, you have to learn about the analog electronics parts, right? So the filtered voltage will be powering it. And then there will be enable pin. You need to give the set of voltage. I'm pulling it to high. So it means it will be high. And then this circuit is now activated, enabled. I'm connecting all the ground pins together. Also, I need a data output from this chip. 2 data outputs. This is for some other purpose. This is all these ground pins I'm connecting to the ground, right? I'm not connecting any of the other pins, so that's kind of okay. And then this pin I'm connecting to a switch because I need to pull it down because I need to program it. I need to pull it down to program this chip. So when I do the programming, I need to connect this switch and then I will get my work done. Also, I need some USB connections. This ESP32C3 has a USB inbuilt, so I can directly connect the USB D plus and D minus pins. So that's kind of pretty much the microcontroller part. And then I need the USB input power coming to this. So when I plug in a USB, this LED will be lighting up. And then I will have this chip will be charging the battery. So that's I have named here. And then I have this battery connector. So it has a 2-pin connector, 4-pin connector, I think, based on the customer requirement. And then we have a USB-C connector as well, this pin. And then 3.3 voltage regulator, because the battery is going to be in somewhere like in a different range. So I need this chip to get whatever the battery voltage is and then filter it to or regulate it to 3.3 voltage. And finally, I have an LED array, RGB LED array, addressable LED arrays. So it's getting data, connecting everything together. So how are we going to connect it? That's up to you. You have to get that part going. And then there is a vibration motor in this circuit board. So that's going to work. Okay. Now, if I look at this PCB, I'm not sure if it will load. Fine. Let's see. It's kind of loading. Let's see. Yeah. So this is the final PCB that I designed for this customer. Okay. Now, can I see this 3D view? I can see it, I think. Okay. So this is the final part. Now I have this ESP32 board here, inbuilt. I have this USB-C Type-C connector here. I have this battery connector here. I have this vibration motor here. Other components, there will be a switch here. I will press this during the bootloader programming. And then other components here. So this is a two-layer board. There is a top layer and the bottom layer. In the top layer, I have these components placed. In the bottom layer, the displays are placed because this will be some kind of a watch. What kind of watch? For example, LED display watch. Not this thing, the LED, or should I? Yeah, something like this. You see here. You see here. So these LEDs will be sitting on the top and other components will be going below, right? I am using two-layer circuits here. So how do we achieve this kind of design? So the customer wanted a round circuit. So we need to decide the shape of the circuit. So this temperature. So first of all, I'm going to place some the board outline. Sorry, the board outline. So let's say we are going to design this board in a square shape. So if I view the 3D, I can live preview it. So this will be our square shape board. Now I'm going to place, because the other components haven't been loaded, so I'm going to import all the changes from the schematic, apply changes, everything will come. So I mean, in the actual design, there will be a lot of other components. For example, these components. the lot of battery, power management chips, inductors, capacitors, resistors, everything will be there. But in the quick preview, let's say this microcontroller needs to be there. But when it comes to this microcontroller, the problem is the data sheet. Okay, if you look at the data sheet, you need to be, I mean, you can't design a circuit without looking at the data sheets, okay? They will be telling you a lot of things. When you place this board in your circuit, when you place this ESP32 in your circuit, there are a lot of things that you need to consider. One of the most important thing is, I'm not sure if it has this, I think this will have it. You see this chip is having an antenna inbuilt, right? There is a reason we are choosing this instead of something with this port. You connect external antenna here, or you can connect your PCB antenna here. But we are not going to choose it because of the reason. We will look into it later. Okay. So this thing, the one comes with an antenna. We are going, let's see. Yeah, PCB layout recommendation. In our PCB, how are we going to place it? So that's an important thing. We have the image. Yeah, you see here, the antenna area, what they are saying is, okay. So this is the copper area, the electrical conductive area, wire for thermal area, right? There is a clear image usually they give. I'm not sure, let's say, yeah, this is the document. Just in the actual technical documentation sheet, they usually mention it. You see here, this is the diagram. You can place the antenna outside the circuit, not inside the circuit, because this antenna, if you place it on the copper surface, it will reflect the waves, right? So you can't place it. You need to refer the actual technical documentation to see where you can place the antenna. So in this thing, you can't place it somewhere here, but you can place it somewhere outside, right? But for in this design, I had to place it in the center of the circuit because I need the motor at the edge of the circuit. So how do I avoid the waves from reflecting? I made a small cut on this circuit board. How do we do that? We can use this, I think this is the one. Slot region. I can draw something like this or rectangle and then place it here. Right? And then I can place the antenna inside this. Right? And then if I see this 3D view, you will see the hole. You see this hole? There will be a small slot cut out from the PCB. This copper area is removed now. So this antenna waves, the Wi-Fi, the wireless, the radio frequencies will come out of this hole without having to reflect from this. So how much size, the width, how much the distance from this edge to this hole, those are defined in this data sheet. So you are going to refer it when you design it, okay? So I have covered everything. Also, you are placing other components here, and then, for example, let's come here and place other components. This connector, this screw terminal, you can't put it in the middle of the circuit because you're going to put wires here. So this wire will not be going, should not be going over other components, right? So you're going to put it at the edge of the board. Now, let's see 3D print. You see here. Now it's coming to the edge of the board. If we displace him here, the wires will be going over the board. That's not recommended. Yeah. And then likewise, you're going to place a USB-C connector. If you put it somewhere here, you can't place it over any other component, right? You're going to place it somewhere here. But the customer says, the sensor connector has to come here. You're going to place the USB charger to the other side, and then this BMS chip coming here. Some rough, just a quick demo design. Okay, this comes like this. Now you modify the circuit board because that's too large. So you are moving the components and then getting your things done. So that's a quick way to make it. So now we have the final design done, right? But the thing is, here, we need to actually connect the lines. That's what we call routing, okay? We finished the layout part, where the component placement part, okay? The layout, the entire PCB layout consisting a lot of steps. So first step is component placing. We need to place which components where, which layer, top side or down side, the bottom side. Also, we need to place components so that the connection, because if there is a connection, has to be coming from this pin to this pin, and there are no other spaces because it has to be a physical line from here, right? So if there are no space, you can't route it. You can't actually connect it through the copper. So you need to place the components accordingly. So that's how I have placed components here. So you see here, this connection, this pin is going from here to here, all the way through here, and then connecting to the other components here. You see this, right? So if there are no space in this area, it will be a problem for me, right? Because also I have cut down this region. There is no copper here, so I can't place any routing signal lines through here. So that's some important part, right? So there are a lot of things you need to consider when you actually make a PCB design. So that needs a specific separate PCB design workshop to teach you all this stuff. So this is a quick demo. There are a lot of videos in the YouTube. So the thing is, I'm going to teach you now how to order this PCB, right? So we are not going to, whatever the software you use to design your PCB, for the manufacturer, you're not going to send the source file, right? Because this is something that is the property of our company, of our team, right? We are not going to send the source file. Rather, we are going to send the files called Gerber files, right? Now, export. Now you have the files, PCB fabrication files, the Gerber files. And then you also need a pick and place file, and then need a bill of material file. I will tell you what are these files. The fabrication Gerber files is going to be it's going to tell the manufacturers what layer is going to be there. For example, this board cut, right? We are going to cut a copper board to this circle area. So this will be in a layer. That will be in the Gerber file. Where to drill these holes, where to cut out these regions, where to place copper, where to remove copper, okay? Where to cut these holes, right? So all these things are defined in this Gerber file, right? That's what we are sending to the PCB manufacturer, PCB fabrication part. Once we have this PCB, right? Once we have the PCB, we will get only the PCB, right? So this kind of PCB, printed circuit board. We will not have any components on it. So that's what we call assembling. We are going to place our components, solder it, and then finally do some test. So you can either choose to manufacture the PCB from a company and then solder it to yourself, or you can ask the company to solder it as well. For example, this circuit, let's see, we are going to, can we order this? So what I'm going to do is, I'm going to this PCB, and then export, order PCB at JLC PCB, right? So I'm going to do DRC, ERC, these are important things. We don't have much time to cover all of this. So I'm going to continue exporting. So now this will export the Gerber files and the pick and place file. What is a pick and place file? It's going to tell which component is going to be placed where. The because during the assembly, this is now Gerber files will give the PCB PCB board for us, but to place the components, because that's something I can show you. Pick and place. We see these kind of machines, right? So here all the components are placed. This is going to pick a component from here and then place it on the PCB. And then we will solder it, okay? To do this, we need to load this machine a file called PNP file, pick and place file. Load which component, 1, 2, 3, 4, 5, 6, which component, and place it where? The XY coordinate, right? That's also another file we are going to get from the export, the pick and place file. We need to give this to the manufacturer. And finally, we need a bill of materials. What is the bill of materials? What are the components? What are the part numbers? Where to buy them? What is the price, etc. So this is needed to purchase these components from the supplier. So we use the Gerber files to make the PCB. We use the bill of material to purchase the components. And then we use the pick and place files to place whatever the components we have bought on the manufactured board. So these are the three important files we need. Hope you have understood it. Right. Now let's try to order this. There will be a couple of steps. You can directly order from JLC PCB. You can directly order for a fairly low cost, but the shipping charge will be a bit high because of there are problems with the import restrictions and things like that. Okay, now we have the board ready. We will be able to test it, right? Now, once we finish all this testing and everything, there will be a big problem. The enclosure design. Design for manufacture. The enclosure design. What is enclosure design? Is PCB enclosure design. You see, once we have the board ready, we can't give the. With that, if you turn on precisely. So once we have this board ready, we can't give the board to the customer. Rather, it has to be covered by an enclosure. Why? For protection from the water, also some interface from protecting the user from the electrical shocks, right? Also allowing to connect some other components, the devices, external peripherals. There are a lot of reasons we need enclosure, right? So what is the requirement for this enclosure? That is going to be up to the your device requirements. For example, if you are familiar with new latest mobile phones, you see they have taken out the many parts. For example, they removed the feature of the battery replacement. You know, in earlier phones, what they had was you can remove the back cover and take out the battery, put a new battery and install. But now, all the phones are now like water resistant, right? So for that purpose, they say they removed that feature. They kind of glued the back cover completely and they put the battery inside fix. No, you can't remove it without having to remove the back cover. Remove the glue, right? So why do they do it? Because of the requirements. Earlier, the requirements was to have replaceable batteries. Now, no, you don't need replaceable batteries. So we are going to seal it. So the enclosure design is now seal design. Earlier, they had memory card slots on the side. Now they said, for some reason, we are not going to give it. That's some of they have their reasons. But so what I'm trying to say is, your purpose of designing enclosure is going to be what are the requirements, what are the types you're going to have is going to up to your standard. Okay. Now let's okay. When it comes to do the enclosure design, we need to think about something called design for manufacturing, not only for the enclosure and the entire product as well, design for manufacturing. Earlier, we talked about design for testing, the DFT, right? The design for testing. We said we need to design in order to be able to test the circuit, right? But when it comes to product design, the final design, we need to talk about something called design for manufacturing. What is manufacturing? You can decide whatever the thing you want, okay? However the way you want, you can design it. But at the end of the day, it's going to go to the company, like, for example, we have Lanka in Sri Lanka, right? These are the companies, they are going to do the manufacturing. So there will be people sitting here or standing here and then finally doing your work, right? So you designed in a way that is very hard to do this kind of assembly, then your product will fail or it will become very expensive, right? If you need, let's say, 10,000 units in a week, you need to design your product so that it is easy to manufacture, right? That's what we call design for manufacturing, right? The design for manufacturing, right? For prototyping, you can 3D print it, put it inside and get things done. But for industrial level manufacturing, you need to go beyond it, right? If you design your enclosure thickness to be very small, it might break during the manufacturing process as well, right? If it is, because it's also going to go through some high temperature manufacturing steps. If it is something you designed in a way that it melts or fails during high temperature processing, your manufacturing will fail, right? The tooling is going to be something machining or CNC specific thing. They need a mold, they need a machining tool, right? So they need to make it specific for you. So if you design something that needs multiple molds, multiple tools, then it's going to cost you a lot. So if you can design your product, right, final product, then in a way that they can reuse whatever the other components they have, your manufacturing cost will going to be very low. Also the clearances, better antenna button, they have to fit together. For example, this woman, the lady is going to place components and use screws here. Let's say this woman is using, there is a screw here that needs to be, it needs to be fit to this component, but you place another component here that is blocking the path, then there is a problem, right? They have to remove that component, finish this work, and then place it again. So you need to think about the entire assembly process, entire manufacturing process before you actually deciding to, making your design, right? So we have been doing this for a long time, and if you have any, like if it's boring or if I have made anything unclear, you can ask in the middle as well, right? So we have seen quite a lot of things on making an actual thing that you can send to the market, send to the actual people to use. These are the lot of important things you are going to consider, right? Okay, next thing will be production validation and firmware. Uh, Let me see. So this will be about firmware. I will come to this again. And then IoT protocols, the regulatory hurdles. Yeah, this is important thing. Okay, now let's see. The proof of concept, you finished it, breadboards, development kits, component selection, you finished it now, and then you come to the engineering validation test, you make your custom PCB, 3D printer housing, you write some firmware, get things done. It's working now, okay? And then you go for the design validation test, environmental test, certifications, ordering, for the bulk ordering things. So this will be the next step that we have covered half of this thing. And then we will go for the final things as well. So at this point, before we go further, do you have any questions, or do you want to like ask anything, or you want me to cover something else if you think this might be something unnecessary, or so what do you think? Because so far I am the only one who have been talking. Anyone would like to give some words? Any questions, any feedback so far? I guess even here, or like I think our scheduled time should be ending in like, I think we can finish it in 10-15 minutes. Before that, I will quickly go through one of the most important. I mean, we can't cover everything. We can't cover entire PCB design thing. We can't cover entire firmware design, embedded Linux or RTOS, everything, right? So I will quickly grab into those stuffs and we'll try to finish it. Okay. So let's talk about the firmware. So when it comes to firmware, you finish your PCB. Now you want to write the firmware for that. So you need to decide, are you going to go for bare metal or are you going to use RTOS, the real-time operating system? I'm not sure if we have time to go through this entire thing, but yeah, I don't think so. Let's talk about this important thing, OTA updates. Okay, so OTA, you have a very good product in your hand, the mobile phone, right? So that's basically an embedded device, right? They design the circuit, they design the enclosures, put the battery in, everything connected. Then they gave the phone to you, right? Now you have the phone, the firmware is already loaded in it, right? What if they want to give you an update, a firmware update? And then what will happen if they say, hey, bring the board, bring the phone to us, the company, so that we can plug it to the JTAG adapter or the USB adapter and write the firmware? It will be bad, right? We can't do that. If it is let's say an embedded device like a GPS tracker, GPS login device for your vehicle, if you want to update the firmware, you can't get the physical hardware to get the firmware updated, right? For example, yeah, this has to be done over the air, right? If it is connected to the internet, you should be able to do it wirelessly. You can't access the device that is far away from your manufacturing plant. The customer is using somewhere else. You can't call them back. So this is an important thing you are going to support in your hardware design, over the air updates, right? So when you select components, you need to make sure that these components are going to allow you to have over the updates. That's an important thing. So how are you going to manage over the updates? How are you going to have the bootloader to support this, right? This is important thing. Okay, the next thing will be the protocol selection. I think we don't. So I think I'm going to wind up in like 5-10 minutes, and let me talk one important thing before
before finishing it. Okay. So this is the important thing that I'm going to be talking is certification, right? Do you know, like, now you have your electronic engineering degrees, right? You can design any circuit boards. Have you seen the prices of some devices? For example, if you go to the medical devices, let's say in a hospital, you might even see in the news, someone donated this many million rupees device to this hospital, something like that. You might think, why is it even costing that much of money to buy some simple device? The device you can design by yourself, but it's costing that much in the market. Why? Because these are regulated industries. You can't design something and send it to the hospital to use it. The hospital will not use it until it is certified for medical usage. Do you understand what I say? You can't send a device to be used in the food industry until it is certified by them, right? Same thing. The device that we talked, the temperature logging device certifications. There are certifications. What certifications? There is a good certification number, I forgot. Yeah. There was a device. There are certain standards. There are certain protocols. There are things, right? Cold storage monitor. Yeah, EN 12830. What is this going to tell us? Because if you are designing this cold storage temperature logging device, and if you want to sell it to the actual customers, they will ask you, does your device have this certificate? Why? They need to make sure that this device is compliant. This device has all the set of requirements to fulfill our purpose, right? So that's what we have. EN 12830 standard. Because in many devices you can flip it and see the label. There will be you see CE compliant, CE letters are there, right? So this standard, the 12830 standard, will tell you define the technical and functional requirements for air temperature recorders used in product transport, storage, and sales. So if you are designing this temperature logger for the transport devices, we need this certificate. So what is this certification? The standard is going to tell us that entire document, right? So you see here. Okay, now temperature measurement instruments. That's the one that we are going to tell. So I think we can't even access it directly without having to buy it. Okay, they will buy it. So you see the entry level is kind of flat. You have to pay for it. Now how do you cover this charge? You will add this to your product price margin. Now your price, you can design the product for a low price, but now the certification cost is kind of coming in. So you add the cost to this product level. So that's how this certification. So once you submit this for the certification for this by these companies, they will charge you a lot of money. They will take some of the products from you. They will do some test. They will check against all the standard values, right? If it is matching, if it is compliant to all the set of requirements they have, right? For example, this audit trail, let's say it will tell how long the data has to be able to be accessible, right? For example, scale of measurement, how much of scale can you measure from this device, right? The softwares, about the parameters, about the service provider, who are we going to provide this service? And then what kind of cloud computing are you going to connect? Everything's listed in this standard. If your device doesn't have any of this thing, then your device will not get this certificate. You can't sell it to the actual market.
You can sell it to the gray market, of course, but if you want to like send it to the actual market that is using it, the corporate market, to the export market, you need these certifications. So that's why we need these certifications. These are expensive. That's one of the very big barriers in things. One of the easiest ways we can get rid of, or take down the cost is by using pre-certified components in our circuit. For example, if you're having some wireless connectivity in your circuit, it has to have RF certified components. If you design your own antenna on your circuit, you need to send it to the certification board, pay their money to get it certified. But if you use the predefined or pre-certified device from from companies, they already did that hard part. Right? For example, the expressive ESP32, C3, WROOM certified. You see, they have the certification already done. The C3 board has the certificate. You see, they have FCC certificate, they have FCC certificate, 5G certification is done, SRRC certification is done. They have everything ready. So if you buy their component and put it in your circuit, you can clearly say our part is like done. We don't have to certify it again because this company is already certified, right? For that particular purpose. So these are some important ways you can get your product to the market quickly. So I think I have covered some important things. This time is very low and I couldn't cover much thing. So each of this is a separate thing. You can learn a lot. If you want to cover the certification part, that's a very long journey of learning a lot of things. If you want to learn about PCB design, that's going to take a lot of time. If you want to learn about enclosure design, the 3D CAD design, that is a separate thing, a separate path where you can spend a lot of time to design 3D printing, actual machining, tooling, manufacturing, CNC stuff. That's different areas. Wireless protocols, IoT protocols, that's a different thing. So each of these areas is going to be very large, very vast, and it's going to take a lot of time. So I hope you guys at least got to know some stuff that there are things like this, and you can explore these areas on your own time, on your own effort. I hope this is something I have covered enough. I'm not sure. I'm expecting your feedback. So far, I have been talking alone. I'm not even sure if if you can hear me or not. Like, anyway, so I'm going to be winding it up. I'm going to wait for your questions for 5 minutes, and let's see. Yeah. So yeah, anyone? Guys, are you there? Oh, the organizers, what's the plan? So
Yes, so we'll wait for any Q&A for the Q&A session if our audience has any questions, and we'll move on from there.
okay, all right, yeah. So apart from questions, others, what do you think? So were you expecting this, or were you expecting something else to get from this? I think we have something in the chat. Yeah, I can share the slides. Someone asked, yeah, I will share it. I need to edit this out. Yeah, I will edit this out and share it. Yeah. Anyone else?
Guys, if you have any questions that you would like to direct towards sir, you can either turn your mic on and directly ask it, or you can use the chat and send a message to the chat if you prefer that. Either way, questions are welcome.
Okay, Kasun asked, sorry. Yes, also you can share your experience. Like, have you designed any product? Have you done any prototyping for your projects? Have you worked with any production level products with some companies during your internships, or someone maybe like freelancing works you done? So, what kind of problems did you encounter? Have you had any experience like that? Or do you think, do you want me to like cover something else? Like, do you want me to explain some other problems that you might have gone through? You can unmute and ask, or if you want, you can drop it in the chat. Okay, so someone is asking, can computer engineering students get internships in electronic field, undergraduate 6 months? So this is up to the actually this engineering market is kind of weird, okay? So there are people working in software and industry, but they did electronic engineering degree. They did electrical engineering degree, but they are working in software development. There are people with computer engineering degree, they work in like electrical areas. It's kind of strange, okay? Because the because of this, what you see here is you learn computer engineering, but in your free time, in your own time, you learn some circuit design. You learned about electronic testing, electronic design, electronic te testing development, or hardware design, or firmware development. You can use that skill to get your internship. It's up to the company, okay? Whatever the company you reach out, tell them that you are interested in, you have this portfolio, you have did some projects, you have done some online courses, you have this thing you need to learn. So you express your interest and say, yeah, I need this. They don't actually look at your degree usually, most of the cases, because internships, people need interns, okay? If they see you have the skills and interest to work in, they will definitely take you in. So that's what I have seen in the market. So yeah, if you're interested, go ahead. But computer engineering is kind of in demand. Usually electrical people comes to the computer engineering works, not the other way around, because of the demand, the salaries in the field. Because if you look at the electronic industry in the Sri Lanka, it's very rare, right? There are no product development companies much here. Um, so it's very rare to find companies. There are some startups here, you can reach them out, but they are working for overseas customers. It's very rare that we have product development companies. There are companies for assembly, PCB manufacturing, for example, GPV is there, various systems there, Toslanka is there. These companies will hire test engineers, hard the circuit design engineers as well, right? But not the product development. They use these engineers to develop some test hardware for the products they are manufacturing for. We got another question. When using KiCad, what are the most critical factors to consider during the PCB routing and manufacturing planning stages? So I think this question is not specific to KiCad, rather this PCB routing and manufacturing plan, right? That's the most important thing. Because if you look at a actual product development company, you will have the thing is like you will have separate engineers. For example, the circuit design engineer will be someone who is only doing the schematic work. The PCB layout engineer, there will be a separate guy, expert in that field to do that thing, okay? He will be doing the component placement, the RF circuit, high-speed circuit, the routing, everything will be there. So based on the thing, because that is a huge part in the PCB design. Because, for example, if it is a small circuit, it doesn't need high-speed signal lines. So let's say, for example, you are designing a motherboard, computer motherboard. It has some high-speed signals from the CPU to the RAM. It needs to have some high-speed signals, right? So that's going to be you can't route it in a normal way. You need to match impedance, right? The RF routing, RF circuit design is kind of a very vast area. There are a lot of things you need to learn, right? So you can refer some online material. There are a lot of YouTube tutorials, for example. I can show you this guy. You can follow this guy. I think I forgot his name. Try to forget his name, but yeah, this guy, Phil Slip. If you follow this guy, you will learn a lot in PCB design. Okay, so he's designing a gigabit Ethernet adapter here. This will have high level of high speed signals. So you're going to learn a lot in there. And also, how about some RF circuit design, right? How to learn PCB design. This is an important video you can refer, right? Antenna design. So when there is an antenna in your circuit, the routing part is going to be completely changing your plan. Okay. And then manufacturing. So if you actually go for the manufacturing stage, what happens is usually when they receive the order, they will email you and asking, are you everything is fine? Or they will say, is this component going to be this way, or are you going to rotate it to 90 degree? Is it fine? They will ask a lot of questions. Also, they will say this component is not available in the market. Is it okay if we find it from someone else? Because there is a big Chinese market. For example, if you open up a LED bulb in your home, you will not see some standard chips in there, right? You will see some chips, you won't even find data sheets. What they actually do is there is a Chinese market. In their market, what they do is they go to they have shops like the shops we have in Beta. They have in the Shenzhen Chinese market, there are shops, wholesale shops. They go there, purchase the chips and put it. We don't even have the data sheet for it, right? So there are that kind of gray market is there. So you need to understand this market so that you can take the price down, etc. The manufacturers will say, we can't find this component. Can we use this component? So you need to find if it is matching, if it is a good replacement for this, right? That's one thing. So I think, is that what you ask, or if you have any, if I things, please let me know. And the next question is, how do we prove of electronic knowledge in CV? What engineering specialist students can show their GitHub? Okay, that's an interesting question. So he's asking GitHub, can what software engineering specialist, software engineering specialized students can show their GitHub. How do we show our portfolio projects as electronic engineers? That's a valid question. I'm going to say you can use GitHub. For example, I show you this guy. I'm floating this one. He has GitHub. Let's see, have the GitHub page. Okay. One thing apart from GitHub, you can use this OSHW, Open Source Hardware Lab. Here, you can publish your own projects. So this open source hardware people, they can come and see your projects. You can use this page as your, for example, if you come here, there will be a lot of projects done by others. Let's say if you are this guy, you can come to your profile and see whatever the projects you have done here. This is one of the good place to showcase your project. So you can put this link in your CV so that others can check it. That's one thing. Other than that, you can use GitHub, okay? GitHub. um, uh, hardware. Something I'm going to say something. Open source hardware. If you come here, you can see uh, a lot of open source hardware. For example, Arduino is an open source platform. You can just I'm not sure if they have the GitHub ones here. You can actually, you see this guy has this repo, right? He has listed all his projects here. If you come to this folder, you can see the firmware files. Yeah, you can see the circuit files. You can put it somewhere here and then something like that. Okay, so that's another way. Either you can use OSW hardware, or the open source hardware platform. Also, you can use the GitHub as well. You can put the screenshots of the images and then include this in your CV or LinkedIn, whatever. The third option will be to have your own own portfolio website. I'm just randomly choosing some guy, okay? So he's a computer science, electrical engineering guy. He has his portfolio project. So he listed out all his hardware products he has built. So he can include his project because he used GitHub for this, okay? If you know how to generate some websites like this, it is fairly easy. You can use GitHub to get your portfolio website. So each of these will be his portfolio project. So he has listed what are the components, how he planned the firmware, everything is there. So you see here, I can show his actual GitHub profile. You see here, all his repositories are here. He used these repositories to generate this portfolio website for him. So he can see he can actually have his own portfolio website. You can build one of your site. I can use this URL in your CVs, right? Did that answer your question, Kasman? And then there's another question. What's the current job market like for embedded system engineering in Sri Lanka? So we have a question. What is the current job market for embedded system engineering in Sri Lanka? To answer because it's kind of growing, but not in a fast-paced growth. But I can't say there are not much opportunities. At the same time, I can't say there are a lot of opportunities. It's kind of difficult. Okay. The most important thing is we don't have product development companies in Sri Lanka mostly. There are small startups coming in. For example, as you asked about embedded system, I can show you this company. Inivos Global. Okay. This company is kind of recently they are getting some hit. They are making firmwares for European cars, for example, Volkswagen. For those cars, these people are building firmware, the embedded system people. These people are sitting in Sri Lanka. Okay. This company is hiring people. Yeah, you see here. I'm not sure if this is the right company. Let me see. This is the right company, I'm not sure. Maybe I opened up a wrong company. And it was, yeah, I think that's the company. They are hiring embedded people, all right? You see, they are asking embedded people working for automotive hardware. There are companies like this, okay? But not much. These people are hiring, okay, 10, 15 people. It's very competitive. There are companies, for example, Vega, but they are also like kind of saturated. They have people already. They might get some interns, some people time to time, right? So there are only a set of small number of companies are there, but the best way will be to, if you want to work in this field, you have to go to like Upwork maybe. You can find some clients, work on your own. There are like electronic model design, these kind of PCB design works are coming all the way. You can learn, you can earn KiCad PCB layout, low noise, mixed signal EEG board. This will be like requiring some advanced routing skills. That's why they have listed for this price. But this is very competitive. You see, there's already proposals, 5 to 10 proposals done. You can try this if you want. But Sri Lankan market is kind of tough, right? If you find external like overseas client, then it's good. Otherwise, it's going to be tough and very competitive. Did that answer your question? And then anyone else, anyone have any questions? And how about this session? Was it helpful? Like, was it useful to you, or did you guys expected something else? Or anyone else? Anyone want to ask something? You want to discuss something? Share something with me? Also, there's this website, Hexter. You can post your hardware projects here, right? I forgot. There are like a lot of people posting their projects, sharing these projects. Also, they conduct contests, okay, competitions. You can go here. That's one of the important, interesting thing you can try it out, okay? Contest. And then you come here, there are like competitions happening. You see this competition happening. You see here. Sometimes they even give you free hardware for this, okay? They will send you this hardware if you apply for this. If you send your proposal, they will send you this hardware. And then you can see the prices. The best in show, $5,000, $3,000. There are things. Anyone else? Any questions?
So since our allocated time is over, I think we should move to a few please. Thank you.
Yeah, maybe we will we'll stop sharing and then we can wind up this session. Maybe.
Thank you.
Yeah. So, okay, thank you very much, guys, for sitting through this session, and hopefully we'll meet next time. Or hopefully, I'm wishing you a good luck on your career and on your education. And thank you, Kasun, for your feedback. Thank you, organizers, for organizing this session. And yeah, see you guys next time. And then until then, goodbye.
Thank you very much, sir, for that inspiring session. I'm sure all of us had something to learn from the past 2 hours.
I hope so.
And as we conclude today's workshop, I'd like to, as we conclude today's workshop, I'd like to express our heartfelt gratitude to Mr. G.S. Umair Ahmadh for delivering such an informative and engaging session and for patiently answering all the questions raised by our participants. Your expertise, practical insights, and real-world applications have given us a deep understanding of advanced IoT technologies and productive. And we truly appreciate you taking the time off to do this. We wish you continued success in all your future endeavors. And with that, we come to the end of today's workshop. We would like to again thank our mentor, Mr. G.S. Umair Ahmadh, for dedicating his time for this effort. And we also extend our heartfelt thanks to all the participants for enthusiasm, active engagement, and continuous support throughout the session. and your participation has truly made it meaningful that we held this session today. So we hope today's workshop has expanded your understanding of modern IT technologies and inspire you to do more as engineering students out there in the industry. And thank you all once again for joining us today. Have a wonderful evening, stay safe, and we wish you all the very best in your future.
Okay, yes, thank you. Bye. Yeah. Good night, guys. Bye.